Good afternoon, everyone. I hope you had a nice 10 minutes resting break. Very happy to be here today. I would like to thank Rick for thinking about me regarding the problem solver session with eC-CLEM, the software we developed together with Perrine Paul Gilotto to address image registration and make it as easy as possible. I put the picture of me here because I think it will make it a bit more let's say user-friendly or friendly in general, so that you see who I am, for those of you that wouldn't know me. I know that for you it's about middle of the afternoon, early afternoon. For me it should be about 4 o'clock in the morning. That's why I've been asked to register this presentation, correlative microscopies in a very broad sense. You might have heard about light microscopies, epifluorescence confocal, palm-stormstead, light sheet microscopy, multiphoton microscopy. You might have heard also about electron microscopies, whether they are transmission or scanning electron microscopies, whether they are in cryo or in plastic mode, whether they are in 2D or in volume EM. You might have heard about image correlation in X-ray microscopy, but it's also an option that you could see in atomic force microscopy or PET scan and NMR. All of these techniques are very interesting, but taken individually, they usually bring one information of interest. Ideally, you would be able to correlate those images of the exact same sample, and then you would multiply the benefit of each of them. So, in general, light microscopy, because I will focus on light and electron microscopy, light microscopy comes in multiple channels. You have very common 2D images with only one channel, but you can easily have multiple channels depending on the number of proteins you've been tagging. But you can also have dynamic information having a fourth dimension, and eventually you could go in 3D imaging, making it a 5-dimensional type of data set. Electron microscopy, on the other hand, must be quite often XY dimension, but nowadays we have a lot more of Z information, whether we use tomography or volume electron microscopy by slice and view technologies. Sometimes you also have chemical electron microscopy that will bring you some multiplexed information. And usually the time you're looking at your sample in electron microscopy corresponds to n+1. If you were doing some live cell imaging. So there are a few challenges in registering images. Some of them are practical, and you've heard about them already in the past few days, which is about finding back your samples. The coordinate transfer are a big challenge. But you also might want to identify homologies between modalities to be able to say, well, I'm looking at the same sample or not. And then sometimes you want to go quickly doing a manual registration to have rapid information and make sure that you're doing the secondary imaging on the right spot. All of these comes also together with mathematical challenges. One of them is to identify a point of interest. You need to localize common features or fiducial, and you might localize them with some error. The second point is you need to be able to target the registration error. So basically, you need to make sure that what you're looking at is statistically relevant. And you should be able to track the registration accuracy across time to make sure that you're looking at something which is a right overlay and not completely random images. There are also some challenges about the computing and the processing. 2D registration is rather easygoing with any computer. But as soon as you go to large data set or 3D data set, it becomes complicated, and automatic registration is also a significant challenge in image processing. And last but not least, you have to apply the transformations you've calculated, and you can have multiple ways of doing that. You have the question of interpolation of your data so that they match each other's resolution, or you have the transformation of the models. And finally, applying the transformation in 3D is not that straightforward. So for that, we developed eC-CLEM, a software which is dedicated to image registration in 2D or in 3D, using all of these models and mathematical models. And it comes together with AutoFinder. AutoFinder is designed to do automatic registration, assuming you've identified homologous points in both datasets. So Before going into the practical aspect of eC-CLEM, I'd like to introduce some of the mathematical challenges which are underlying. The first thing is the fiducial localization error, which is inherent to any real data. If you would be in an abstract data set, basically a point is localized by x, y, z coordinates. In real life, it's much harder to find out the exact center of mass of any object. Whether you're doing fluorescence microscopy, where anything, because of the point spread function, will look like a blurred large area, even in super resolution microscopy. And the association of this pair of points that you can have and the imprecision you have in localizing the center of mass will impact the general distribution, and logically you will be unsure of where is the center of mass of your entire volume because of the imprecision of the points here. So every single point is identified as a statistical capacity of being underneath this Gaussian distribution. Quite intuitively, you would understand that the more points you have, the lower the statistical localization error becomes, because they will compensate for each other. So these kind of things that you've seen in light microscopy also applies in electron microscopy. Those of you that are familiar with tomography will realize that sometimes finding out the real center of a gold bead might be quite challenging, and you might correct it. Whether you're using a Gaussian fitting or not might not always be that perfect. And so the same applies as to light microscopy. The center of mass of your point of interest that you think is the same in both modalities is not always that straightforward to find. And so if you combine the imprecision of finding out the center of mass of the object in light microscopy and in electron microscopy, well, you end up having something that can be, with the same number of points, could make a different type of registration, as you can see in here. So the idea is to be able to estimate this precision in localization, and then based on that, trying to find out the most stable transformation, so that you can overlay your images and make sure that what you're looking at is corresponding to the same structure. So that's about the individual points we're interested in. But then the distribution of these points on itself is also having a significant influence on the target registration error. So Fitzpatrick et al. Have worked a lot on these problems in the case of medical surgery, where they wanted to make sure that a patient will be accurately treated when you want to remove a tumor or something like that. So basically, he evaluated the best way of measuring the precision in any localization of the sample. I won't go into the details of this equation, but technically, this reveals the way of measuring the precision in any point of the image based on the fiducials you have and estimating the precision of localizing them. In a more intuitive way, the placement of the points is quite important. Let's take the first example here, where we have 6 points which are extremely well spread across the image, and these points have a center of mass near the center of those points. When you try to look at a data set of interest here, close to the center of mass with very well spread points, then obviously the precision you will have here might be much higher. And that's what we see here in this blue line here, where a very few number of points will give you a rather low or high precision, but low avoidance of the center. If you take here a different situation where all the points of interest are extremely centered and the registration landmarks are centered and your point of interest is far apart, what you realize is that here the center of mass remains pretty much in the center of your point, but this guy here is far apart. And the consequence is that you might have a lower precision here because you're far away from your set of points. And that's what we see here in this purple curve, where basically we have a low dispersion of points. The center of mass is fairly strong, but it's quite far apart from the point of interest. And therefore, you will need to have a lot of points here in this narrow area to make high precision far apart from your sample, and you might even never reach an optimized, the optimal situation. In the third situation, the points are displaced in fairly well dispersed on your sample, but then the center of mass of all these points remains far apart from your point of interest, and therefore the precision you will have will take more time to reach the same quality, and you will need to have more points to reach the same quality far apart from the center. Last case, which is quite important, if your point of interest is in the center of mass, whether you have the points which are very close to one another or far apart from one another, you will get a high precision as well. And that's what we don't see so much here on this graph, but corresponds to the gray curve, which is underneath the blue one, the dark blue one. So all of this is quite intuitive on the daily life. But that's quite important when you place your points in image registration, whether you do it in 2D or in 3D. A way of seeing this is, for example, here we've placed all of these points across an image, localizing fiducials, and then what we do is we play with those two guys. In the first case scenario, we place the point number 5 and we evaluate the precision in point number 10. And what you can see here on this graph is the statistical precision we get in any point of the image. So it goes from 69 nanometer in precision to 177 nanometer in precision. This means that something which is in the dark blue, almost black here, will be accurately localized down to 60 nanometers, as something which is in this region here would be accurately localized within 170 nanometers, which might be critical because you might start to mix up different structures. Now, if we do the same data set, the same number of points, but instead of placing the point number 5, we place the point number 10, and we look at the precision in here, you see that the global precision of your entire data set is influenced, and basically it becomes more rounded, and you have the precision remains quite high here, but it's increasing at the bottom near point 10, and it's decreasing near point 5, which makes sense as we've described it before. So because we have this and we have seen this graph with the shadows, we can also predict the registration accuracy in any point. So the idea is to be able to see when you place your point whether they are precisely located and whether you could use that to correct your precision. So with this same equation, we're able to identify the precision of the point here and where it would have been expected to be placed, assuming that all of the other points would be perfect. As you can imagine, as soon as you displace this one, basically it will influence the entire data set, and this one will no longer look exactly the same because you will have changed the balance of your entire data set. So we already see that we have a few sources of error. The first one is the fiducial localization in error in each image. How precise can you identify the center of mass? Here in that case, where do you identify the center of mass of this melanosome, or this one is not obvious. Then we have an error on the computation of the transform, which is supposed to be unique, but then we consider the imprecision in the localization of the point. And then we will see that in the next slides, the transformation basis that you want to use, and sometimes some mismatch in the points that you're placing. But what is very important is that if you want to make sure that you have a structure of interest that you identify, and you want to know when you're precisely located, well, then what you will do is you will say in the software to monitor the precision accuracy of this particular point in light blue here, while you start to place points all around. And in our case, in this data set, we've been placing points in red because each red dot corresponds to a cluster of quantum dots, which are both dark in electron microscopy and very bright in light microscopy. And then as long as we've been placing points, you can see with 1 point the precision in this localization was fairly low, and as the more points we've been placing, the higher the precision in this particular point became. At some point, you decide whether or not you have the precision you wanted to reach. Here in that case, we reach 14 nanometer in precision, which is much higher than the resolution of the light microscope we've been using. And so we can estimate that we have a fairly good localization accuracy. Here, in that case, we can see that the map we've been doing of the entire area is also quite interesting. We have a precision of 38.49 nanometer in precision in the center, while at the periphery it's still 75 nanometer, and the 75 nanometer be more precise than the light microscopy we've been using, since those images were taken on an epifluorescence microscope on section fluorescence microscopy. Then another question comes, which is about image interpolation. You want to have an interpolation between the dataset. In light microscopy, here in our case epifluorescence, but it's true for any kind of light microscopy, the resolution is technically before calculation is much lower than what you would get in electron microscopy. And for a certain number of pixels, you will cover a fairly wide area as compared to electron microscopy. And so this kind of information is critical because whether you want to correlate those images or not will influence whether you will see a big pixel or if you want to interpolate the data. To localize your region of interest, as you've seen here, so you know that this image corresponds to this area. On the other hand, you can also do the interpolation. Basically, you can multiply the number of pixels and calculate their point, the center of mass, and interpolate them on the electron. This is the kind of images you would get then, where basically the image you have here has been interpolated here. And we see that the precision is much finer than in here because we reduce the intensity of the pixels by the factor of the interpolation. So that's one of the key questions, and eC-CLEM always comes with interpolation in both directions. We always match the pixel size of the final image. That's something we decided at the beginning of the project, and this is now a permanent situation. It might evolve in the future, we might see. Now the last question, which is important, is about non-rigid registration. It has been asked to us a lot of time whether we could non-rigid registration. At the very beginning, we were not doing it for a certain reason, is that if you have a mismatch, and this is an example which is made on purpose, what we did here is that we misplaced the point number 2. As you can see, we just focus on the region of interest, but we have already 10 points spread all across the image. And so point 10 and point 7 are placed more or less in the center of mass of our fiducial. Here in that case, you can already see that the precision is maybe not that great. But then this one is voluntarily misplaced. And what you can see is the software predicts that the point number 2 should be actually placed here. If we keep it here and we decide to do a nonlinear regression, what we will do is we will induce a deformation. Basically, we will drag the points away from where they are up until we deform the source image to match the target image. One of the consequences is that you could mislocalize a region of interest. And although in this image it's quite obvious that there's a deformation, you might not see it, but it might be present in it. So now that we've seen all of this underlying mechanism of the machine and how the machine, the software is designed, I'd like to introduce the user interface, which is something we believe is important, as if it's not easy to use, it might not be used at all. What we did is we designed a very simple user interface, where at the very beginning you choose whether you want to compute a 2D or a 3D dataset. You will have some options to pre-process your data. I won't go into the details today, but you can technically remove the noise and you can flatten some images, especially in 2D imaging when you do fluorescence on section. You can, in some cases, apply a previously computed transformation. And then you will choose the image that will be transformed and resized, so the source image, and the target image that will not be modified, so basically on which you will project the source image. Then you have a few items that you have to validate. And here a few things. The first thing is eventually to clear landmark points when you've done some work before, and update the transformation will come later on. You press play and the software will allow you to place points that you have to find yourself homologous point between the light and the electron microscopy dataset. So this is how the things are working. We place a point in the target image and then we allocate it in the source image. Then you place a second point here in the target image, and when it appears in the center of the image, you locate it precisely in the source image. And you do that for 3 points in 2D up until it's able to identify both the transformation and the rotation of the image. And then it will automatically calculate the first transformation and make it similar to what you have in electron microscopy. If you lock the two images together, as I just did right now, then basically when you zoom in the first image, it zooms in the second image, allowing you to efficiently place your point both in electron microscopy and in light microscopy, as you can see here. So this locking option is quite convenient. And you can place points as much as you need, and as you can see, the 6 point is quite far apart, so you have to correct it up until the whole volume is done. So this is the way we've made it hopefully as intuitive as possible. We hope that with this kind of interface, you can very quickly generate. Then another thing that came up very recently and that we did not have at the very beginning, especially when we published the paper, is sometimes to draw lines to register images. You've just seen placing, but sometimes you don't have an identified point between two structures. I take here in this example 2 images where basically the structures here, we can distinguish the outline of our tissue, but there is no singular point to identify. So there is an option, and I will come back to how to deal with that in details, but there is an option where you draw the outline of your structures in both data sets. Then you convert this outline of structures into a series of points by converting the binary to point ROIs. And then you use the eC-CLEM AutoFinder software. You feed the information about the pixel size and the transformation, and all of this is detailed in the book chapter. I'll come back to that point. And then you let the software calculate the optimal transformation according to your outlines. And as you can see, it does the calculation and registers the images to one another as precisely as possible. So eC-CLEM AutoFinder allows you to do something which is a bit more flexible data correlation. It works also in 3D. I'll come back to that point in a few seconds. Then in 3D, it's exactly the same principle, whether you place points or you draw outlines and things like that. It just takes longer processing times. And that's one of the challenges we've been mentioning before and that we're currently working on, is to be able to register very large data set without having supercomputer, because we're researchers, we're not necessarily Google. And so the software works the same, you place points and you do your registration. If you do so, well, you can use the software to register a 2D EM image into a fluorescence micrograph. So basically you would extract the fluorescence slice and place it on your electron microscopy. Or you can place your electron micrograph into your volume, and that would allow you to know where you are in the volume. That's especially important when you're working on biopsies or big volumes and you're doing section picking. Or obviously you could register a 3D stack and combine it with a 3D stack of EM. This technique works pretty well. It takes some time. The calculation is long, and this is definitely not the fastest process, but it works fine. And if you have a computer which is powerful enough, you can do it. If you have a smaller computer, You can also calculate that on bin dataset and apply bin transformation, the transformation to unbin dataset. I'll point in a second. So all of the points that I've just presented to you today were published in Nature Methods in February 2017. It was a work that we did together with Perrine Polgilotto. And we also have a book chapter in Methods in Cell Biology and a book chapter in Neurosciences, in Methods in Neuroscience, presenting the software and how to use it in more detailed way. So I'll refer you to this particular article and this book chapter, especially if you're interested in AutoFinder, where in this book chapter we detailed very precisely the AutoFinder function. Now, if you want to use and install eC-CLEM, you have to first download IC Bioimage Analysis, which is a software developed by the Institut Pasteur in Paris, and it's a Java-based software. It takes some ideas from ImageJ, but it modernized the graphical user interface. Then the very easy way to install the plugin is you go into the search bar here, you type eC-CLEM, and it will just, if you're connected on the internet, it will present one of the, it will present the plugin. You just have to click on it, it will install it, and if you type eC-CLEM a second time, then it will just launch the eC-CLEM user interface. If you click on the question mark here at the bottom, it will open you directly onto the documentation webpage, where we have a list of video tutorials, an introduction to IC, which is not always known, the various ways of doing registration in 2D or in 3D, the registration of a slice into a volume or in both volumes together, how to reapply a previously computed transformation, how to monitor the accuracy, we've seen that before, the pre-processing such as flattening option and denoising, registration using lines. And for those of you that don't like the video tutorials on YouTube and do not want to hear about my voice for so long, there's also the 2D, there are 4 PDFs showing you how to do the same work on step by step. You just have to print it and modify and take your own notes next to your PDF printout. So it's time to finish. I'm very happy to have done this work in the past few years. I have to acknowledge the work that was done together with the supervision of Grassa Raposo and Jean Salamero at Institut Curie, where I did my postdoc, and obviously Perrine Polgilotto, who's the mathematician and the brain behind eC-CLEM. We're now hosted by the INSERM unit in Paris, directed by Michael Schumacher. And we have done this work in the past years together with Nikon and Zeiss, who's been very important partners in developing other technologies. The Francis Crick Institute through Lucy Collinson and the whole team of the EMSTP has been involved in the eC-CLEM development, but also in high pressure freezing. We have a lot of work together with Anat Akiva and Nico Somerdijk at the Radboud University regarding high pressure freezing and cryo-correlative work. I mentioned Zeiss already, but I have to emphasize that they've been supporting our work for the past few years very actively, and we are very pleased to work with them. Members of the team, Cleo Capsel here, my Jérôme Heiligenstein, my father, Frédéric Hérault, Martin Bell, and Laurent Manet, who've been very active in the past years in developing the company and developing the technologies we have, and we're proud to present to you. Our partners in Australia, Trevor Hinwood and Hinsey Company, who's our exclusive dealer in this region of the globe, and has been doing a tremendous job in advertising our technology. If you have any questions regarding the software, our high pressure freezer, or the resin, the R221 resin, which is electroconductive for volume EM, please contact him and we'll be happy to discuss about that with you. And our funders, Seventure Capital and BPI France, who've been supporting financially the company in its growth in the past years. So a big thank you to all of these persons. And with this, I'm very happy to take any questions. I think now I should be awake and I should be in front of my computer. So I should be able to take any questions. Thank you very much.